Hello, wonderful person. Today I'm going to talk about a knowledge graph embedding model which is tailored to learn relation patterns. My name is Afshin Saderi and welcome to my talk. The topic of this presentation is MDE, multiple distance embeddings for link prediction in knowledge graphs. Knowledge graphs are multi-relational graphs which usually are represented using triples. As an example, in the graph of two iterator, Bob follows Paul makes up a triple from two entities of Paul and Bob and the relation with the name follows between them. A knowledge graph embedding model particularly learns the relations in the knowledge graph and predicts the missing links. These models can also classify entities and relations in a knowledge graph. The general idea of these embedding models is to model and infer connectivity patterns in the knowledge graph according to the observed facts. For example, the relations can be symmetric, they can be antisymmetric, like parents of. Some relations may be composed by others, like A is married to B and B is parent of C, will lead to A is a parent of C. And some relations are the inverse of other relations, like B is parent of C and C is child of B. It is crucial to find ways to model and infer these patterns from the currently known facts to predict missing links. However, most of the recently proposed knowledge graph embedding methods have a challenge in learning of relation patterns. For details of these challenges, please check the paper. Previously, it was thought that usage of independent vectors caused inefficiency in learning methods, especially in CP. However, we propose a model based on this idea and show independent vectors can be efficient in the problem if it is correctly formulated. Unlike previous knowledge graph embedding methods, we collectively train and predict using contradictive geometric terms. We also suggest limit-based loss instead of margin ranking loss for knowledge graph embedding. MDE allows modeling relations with antisymmetric, symmetry, inversion, and composition patterns. One of the first distance-based models is translating embeddings. The left diagram shows a triple model by this approach. Analyzing the knowledge graph shows for the most of relations there is an inverse relation, even if not mentioned in the knowledge graph. For example, A is the father of B, follows by that B is the child of A. We also noticed separation of entities becomes impaired if transit learns symmetric relations. We also noticed that in trans-E, reflexive relations are forced to become symmetric and transitive. To target these challenges, we create other modelings of the relations. Each of these geometric modelings lead to a distance function. We see each of these scores have their own set of vectors. Multiple distance embeddings, or MDE, creates distinct simultaneous views to relations with a definite set of latent distance functions. Their independent embedding vectors for each of the distance functions allows aggregation of the contradicting functions. The joint training over the aggregation of distance functions is shown here. We see here W's are hyperparameters for the aggregation and psi is a constant for regulation. When applying the margin ranking loss to translation embeddings, loss calculation of positive samples become dependent to negative samples. There, it is possible that the score of a correct triple is not small enough to hold the score function of the model. To enforce the scores of positive triples become lower than those of negative ones, and keep the positive and negative loss independent, we define the two constants called limits. There, we force that the error in all of the positive samples become less than the limit, and the error for the negative samples become greater than the limit. This method, which previously was proposed for entity matching, showed to be efficient here as well. By learning the W weights and adding the activation function of tangent hyperbolic shrink, we frame the MDE as a neural network. The activation function here adds a nonlinearity, and training the method this way reduces the number of hyperparameters. Here are the evaluation results of MDE in link prediction benchmarks, which shows the efficiency of the model for the task. We also made a version of the model that applies adversarial negative sampling, and we included it in the second benchmark. Here we can observe the improvement of the model, especially on FB 15K237, which produced a state-of-the-art MRR. Countries is a benchmark explicitly designed for composition pattern inference and modeling. It involves 3 datasets with different difficulties. On the most difficult dataset of the benchmark S3, we can observe the improvement of the state-of-the-art by MDE. In conclusion, we propose that multiple views to translational embeddings within independent vectors can perform solidly in link prediction tasks, while independent vectors previously was supposed to cause poor performance. MDE, together with rotate, are the current methods that allow modeling of all the 3 relation patterns. We demonstrate the effectiveness of MDE for link prediction, particularly in composition relation pattern benchmark. Here are the links to the source code, which is PyTorch based and is CUDA enabled. The paper is available in the conference domain, and if you missed the QA session, here is my email address for extended discussion. Thank you very much for listening to this talk.